Okay, so this is about a system of equations very quickly. And another thing I just want to touch, hope I have time. Come on. It's about you can actually do finite volume very easily in multiple dimensions. So in multiple dimensions, you can split a domain like this into cells, and you don't even have to specify what's the shape of each cell. It can be triangles, it can be rectangles, it can be anything. It can be like some people use this kind of a cut cells approach. So basically you can have cells like that. Okay, each cell can have really arbitrary number of neighbors. What are the unknowns in finite volume? It's just the averaged conserved quantity in each of these cells, right? And you apply the conservative form of the differential equation, the integral form, in each of these cells, and the time derivative for the total quantity in this cell would just be a summation of the contribution from this interface, this interface, this interface, and this interface. In the code, you simply loop over all the neighbors of this cell. Compute the flux in between itself and its neighbor, and just accumulate that flux to the time derivative of this term. Yes? No, for example, this cell, it has a 1, 2, 3, 4, right? While this cell only have 1 and 2 neighbors.
Yeah, but in order to use our equations, shouldn't they have the same number of neighbors?
Pardon?
In order to use the previous equations, shouldn't they have the same number of neighbors?
In order to use this equation, we have the equation we want to use is ddt of u is equal to integration over the boundary of minus n dot with the flux, right? Okay, so what is partial omega? So if this is omega, then partial omega would be its boundary, right? So this is partial omega, and we can split it into partial omega 1, partial omega 2, partial omega 3, partial omega 4, right? So then this is a summation over partial omega I of minus n dot f ds. So basically, no matter how many neighbors it has, no matter how many pieces I have to split its boundary, I can always write the contribution from the boundary as a summation over all its neighbors. And the integral over the part of the domain that is shared by this cell and one of the neighboring cells. So as long as I can approximate, in this case, it's no longer approximating the f at a single point. I have to approximate the integral of f over one of these boundaries shared by two cells. So now this becomes my multidimensional flux approximation scheme, right? People also call flux reconstruction scheme, because I have to kind of reconstruct the point-wise values of the flux from an average, which is what I have in the computer. All right, so but like the principle of finite volume works exactly the same in one dimension and the multiple dimensions. The code is just going to be a lot more complex, but the equations are the same. All right, so we'll have a written exam on Wednesday. You can ask any questions if you have about the format. Yeah. The materials specifically we talk about today is actually not appearing in the exam, but like a finite volume per se, we still, it's officially it's included, but like actually it's not. Okay, right. Yes.
So, we talked about it a little bit last time, but basically we should expect it to be like mostly like symbolic derivation and stuff.
Yeah, you are not required to actually write any code or anything.
Pity, that'd be easier.
Huh?
I said, pity, that'd be easier.
That'll be easier, yeah. some point we need to figure out a way to have exams with computers and stuff.
Just let them be like open note and like make the problem interesting like in a theoretical way so that open note doesn't affect the.
But-
Open note, open Google.
Yeah, then you have to have a really hard problem.
Not necessarily, just like something that requires some theoretical understanding of the.
You could have like you could convince MIT to fund you for like some computers.
You could get a Wi-Fi blocker.
Get a Wi-Fi block. Actually, it's an interesting question. Like, how do you test the people's in the age of
Class says you could probably just be honest.